In this video, I'll show you how to solve the ALEKS problem called Identifying Important Intermolecular Forces in Pure Compounds. This is going to give us 4 different compounds. We are going to need to have the Lewis structures of these compounds, but we won't deal with that quite yet. And then it's asking us to check whether or not each one of these compounds experiences dispersion forces, dipole forces, and or hydrogen bonding. So we might be checking only one thing in this row. We might be checking 2. We might be checking all 3. Dispersion forces are also known as London forces. If you're using a different term, they do refer to the same thing. First thing I'm going to tell you is that every single molecule has dispersion forces. So it doesn't matter what it is, you're always going to be checking the dispersion force box every single time. The next easiest thing to be looking for is hydrogen bonding. And now this is specifically asking about whether or not the molecule can hydrogen bond with another identical molecule. And in order to be able to hydrogen bond, the molecule needs to have either a nitrogen or an oxygen or a fluorine atom. And if it doesn't have one of those 3 atoms, it can't do hydrogen bonding. So for example, the NOCl molecule has both nitrogens and oxygens, so maybe it can hydrogen bond. We can't say for sure no. Iodine, I2, doesn't have any of these 3 atoms, so this is not going to be able to hydrogen bond. Dichlorine monoxide, that's going to be a Cl2O. That has an oxygen, so maybe it might hydrogen bond. Br2, that doesn't have any of these 3 atoms, so this is also going to be a no. So once we've gone through that, the other criteria for hydrogen bonding is that the molecule needs to have a hydrogen on a nitrogen, or it needs to have a hydrogen on an oxygen, or it needs to have a hydrogen on a fluorine. And so if we go back to the ones that we haven't ruled out yet, if we look at NOCl, there are no hydrogen atoms at all in this molecule, which means it can't hydrogen bond. Even though it does have the nitrogen and the oxygen atom, it doesn't have a hydrogen. And then the same thing is true with ClO2. There are no hydrogen atoms in this molecule, so no hydrogen bonding. Now that's kind of a bummer. If we did, let's just kind of back up a little bit. Let's say we did have a molecule that had hydrogen bonding in it. So if we were able to check this box and say, yes, there's hydrogen bonding, then in that case, you can also check the dipole box. So anytime you have hydrogen bonding, you can definitely also check dipole. We're not able to do that though. So the dipole ones are actually the hardest ones to figure out. They are absolutely the most difficult. And these are the ones where we need to be looking at the Lewis structure of the molecule in order to be able to check or not check this box. Now I'm going to be using the internet to look up these Lewis structures just to save time. It's a lot faster if we use the internet to look them up. And the first molecule we want to look up is NOCl. And like I've warned you before, if you've watched these videos, you want to be really careful when you're looking up Lewis structures on the internet. You want to make sure that you're looking up the correct molecule because there are a lot of molecules with similar formulas. Sometimes the internet is going to give you the wrong molecule. So I see a few that are the same, so that means I think that, any one of these is probably accurate. I'm going to go with this one right here, NOCl, and I'm going to just copy the Lewis structure down so that we can refer to it. And I'm going to look up, I actually don't need to look up the Lewis structure for iodine, I2, because I know it, so I'm just going to write this. But if you didn't know it, you could just look it up. There's I2. My next one, Cl2O, that's a little bit tricky, so I'm going to look that one up, Cl2O. And looks like there's the Lewis structure for that guy. I see a couple that look pretty similar. I'm going to copy this one. That looks like the easiest one to copy. And you want to make sure that you're getting all of the lone pairs when you copy these Lewis structures. And my last Lewis structure, bromine, I know the Lewis structure for that molecule, so I'm going to copy it. Or I'm just going to write it down from memory. Okay, so once we have all of the Lewis structures for these molecules, we're going to analyze them one at a time. Some of them are going to be easier to analyze than others. And what we're basically looking for to answer this question is we're just answering the question like yes or no, is the molecule polar or is the molecule nonpolar? If the molecule is polar, then yes, it has a dipole. And So if we're looking at molecules, trying to decide if they're polar or not, molecules that have only 2 atoms in them are the easiest ones to work with. If we have a molecule that has only 2 atoms, and those 2 atoms are identical to each other, the molecule is non-polar. So I'm going to cross off bromine, and I'm also going to cross off iodine. Now, if we had 2 molecules, a molecule that had 2 atoms that were different from each other, not identical, this would be a polar molecule if the 2 atoms are different. But that's not the case that we have here. Both of them are identical to each other. So moving on, if we have a molecule that has 3 or more atoms, then we have to kind of think about what that molecule looks like in terms of its 3-dimensional shape: tetrahedral, trigonal pyramidal, trigonal planar, etc. Basically, whenever you have lone pairs on a central atom, that almost always means that the molecule is polar. Not all the time, but almost all the time. Now, I will tell you that if you have only 1 lone pair on a central atom, like we have in this case right here, we have a nitrogen, and there is only 1 lone pair on that nitrogen, and the rest of the molecule is also asymmetrical, this molecule is going to be polar. It's not going to be possible for us to find a plane of symmetry for this molecule. No matter how we try to look for it, there's always going to be something that's not the same, and if we cannot find a plane of symmetry, if the molecule is not symmetrical, then it's definitely polar. So this molecule for sure is polar. This one's a little harder to evaluate because it looks like we can find a plane of symmetry there and then also there, but we have to keep in mind that this particular representation of the molecule is not accurate in terms of its 3-dimensional shape. This is a tetrahedral molecule, so it's got a shape that resembles more kind of like this. And yeah, there is a plane of symmetry in this direction, but if we try to intersect the molecule in a different way, we're going to see that there is not a plane of symmetry. And in order for us to be able to call the molecule non-polar, we have to be able to find more than just one simple plane of symmetry. So since we can find a way to divide the molecule where the lone pairs are just on one side and not on the other, that means that this molecule is also going to be polar. This is a pretty tricky concept. It takes quite a bit of practice to get the hang of this, deciding if things are polar or not. And like I said, this is absolutely the hardest column that you have to fill in this particular ALEKS problem.